Welcome. My name is Ron Papa Schmidt, and I'm the creator of the Net Zero Now YouTube channel. This is going to be video 6 in the relaunch of that channel, and today we're going to talk about the Copernicus Climate Model, and we're going to do a deep dive into that model and how it works. So let me show you how that fits in. When I relaunched the channel, the first video sort of explains just how the new structure is and how I go about creating these videos. But the second video is probably the most important video I'm ever going to issue, and that is, what is our current path? Where are we headed based on what the climate scientists are telling us? And I titled that the Titanic Table. Now, in that, I say, okay, here's what the climate scientists have said has happened to our temperatures, how they've increased. And then here's what their models are telling us how temperatures are going to increase. And then what are the implications of those various different temperature changes. Now, I know when people look at that, there's a lot of people who are maybe skeptical about it or don't think the climate change is going to impact us as soon as I believe it is. And so I thought one of the things I would do to help them understand where these numbers come from and how credible these numbers are is to do a deep dive into those subjects. And so that's why I'm doing this next series of videos here. So the third video was, how do we know, building the climate network, and that shows all the information they collect around the globe to basically do their models that tell you what the actual temperature is and what the projected temperatures are going to be. And then after that, the next presentation was this video 4. We're going to show how actual temperatures are calculated. And in doing that, I thought, well, to help somebody understand that, what would be helpful would be to take probably one of the models and do a deep dive into that model to explain how the calculations are actually done. And when I did that, I found the presentation just got to be way too long and complex. So I decided to really break it into 2 presentations. So for presentation 4, we'll talk about sort of at a summary level what's happening. And then this presentation 6, we'll do a deep dive into the Copernicus climate change model, why that one, it is the most sophisticated one out there. And we'll talk about that in a second. And then lastly, we're going to talk about how they do projections. And this video here would be sort of helpful for understanding what goes on there, because they use a lot of the same techniques. Now, I have to say, this will be, it's a little different than video 2. Video 2, I think every single slide or page that I had in that video is really, really important, and you really need to pay attention to what I'm saying there. This video is not one of those. This is like a detective novel versus a textbook, okay? I think you'll find, if you're interested in this subject, you'll find this just fascinating in terms of how complex these systems are and the amount of data they have and the processes they use to come up with an actual temperature calculation. It just literally blew my mind. I had just no idea how sophisticated this was. And so if you're interested in this subject, why don't you follow me or follow along with that? Most of you, though, may have no interest, in which case I would just stop right now and jump onto another video where the topic will be of more interest to you. But if you are going to follow along, you don't need to pay attention intensely to every single slide and what's on it. You just need to get an impression of, oh, this is sort of how they do it. And it's sort of that kind of a video, okay? So let's proceed. So why the Copernicus model? Well, let me tell you, there's sort of 3 methods that are out there right now. The first one is sort of an hourly model, and that's what Copernicus is. The second one out there is used by Japan. They use the same technique. They call it a reanalysis engine, which means the starting point for these models where they were able to go back and using information, go back through history and be able to calculate what actual temperatures were. So that's a way of verifying the models, etc. And And so the second method that uses the same method as the reanalysis model is Japan, and they do it in every 6 hours. And then you have the other five major organizations that calculate annual global temperature or monthly global temperature, etc. And they do that basically on monthly statistical grids. So that's the difference. Why I chose Copernicus is obviously it's the most sophisticated of all of them. And we'll talk about that in a little bit more detail as we go through this presentation. Okay, so let's start. Well, where did this come from? Who are they? How are they organized? Well, in 1975, 18 European nations agreed to form and fund something they call the European Center for Medium Range Weather Forecast, or the ECMWF. And what they did is they assembled sort of the top computer people and some of the meteorological minds under one roof in the United Kingdom. Why did they do that? Well, it became apparent that with computer technology and advances in satellites and other kinds of things, that there was really going to be, there was a change taking place in terms of the complexity, or the capability is maybe a better word of saying that, of the infrastructure to gather data and process data in a way that would produce more reliable results. And it was really probably too expensive for each company to do that, country to do that on their own, so it made sense for them to form a group to do that, and they did. And this group then, by 1993 and 1995, really had created the first reanalysis model, 1.5. And why these are important, it allows you to construct the historical baseline of which you can compare current temperatures against or measure changes or anomalies, as we talk about. In 2014 to the present, the EU in 2014 basically decided that they were at sort of another one of these major changing points, okay? Computer technologies was advancing rapidly with supercomputers and things like that. Data gathering capabilities with satellites and other kinds of things were becoming infinitely more sophisticated, and their models could really handle and process much more information than they really had available, and they needed that to basically effectively produce more accurate results. And so the European Union decided to invest heavily in building this infrastructure. And at the same time when they did that, they sort of renamed this function to Copernicus, and they created 6 separate subsections of it that uses a lot of the same data. The one we're going to talk about today is a climate change organization, and this is the organization that actually creates the ERA model, and it's the one that does a lot of the reporting. But they use a lot of the same information for the marine area, looking at what happens in the ocean, the atmosphere over land, for emergency response kinds of things, and for security, okay? Now, here's sort of what it looks like today. So if you see this grid in the upper hand corner, you can see the European Commission. And when the European Union decided to put resources into this effort and make a massive funding effort, they continued with the previous organization, the ECMWF. That's hard to say, by the way. And there are actually members that are, I think right now there's actually 40-some members. So there are more members of that group than they are in the European Union. But the European Union now is doing, and they continue to provide funding, but the European Union made a massive additional investment in it. And so now they're sort of driving the approach. And they, in turn, one of their programs they have is the Climate One, and they produce the C3S, which stands for Copernicus Climate Change Services, okay? And they're the ones that create these models. And then the second point is I already talked about that, how they, in conjunction with the European Union here, that organizational change took place in conjunction with the decision to sort of make a massive investment in additional capacities. And the other thing they did at the same time, which is really interesting, I think, is it made it mandatory that everything would be available to the general public for free and there'd be universal access to the information. Now, what you see here is a visualization of the 3D global grid. And what it does, it basically maps in a three-dimensional grid, every single point of Earth is now covered in this grid that goes, not only covers the surface of the Earth, but goes up into the stratosphere. Now let's talk a little bit more about that. So the first thing you have is you have sort of a horizontal footprint. And so as you move from the equator to the poles, that would cover the horizontal grids. Now what happens is it's a similar kind of approach used by the other models. It just happens in the United States they use 24-mile blocks for their grids. For Japan they use 25-mile blocks for their grids. And then for the European Union, for ERA 5, they use 19 by 19-mile grids, or 31 kilometers. Now, the next thing you have is, if you look at the planet, you see it's a globe, right? So what that means from the longitudinal lines, as you move towards the poles, it obviously gets smaller and smaller and smaller. And so what they do to sort of offset that, to make sure that everything, they use something they call the reduced Gaussian grid, which basically, if you looked at the globe, each one of these cubes would be getting smaller and smaller. They basically, through this technique, keep them at roughly 19 square miles. Now, what that means from a resolution standpoint is that using that technique, there are basically roughly 540,000 3x3 or 19-mile cube blocks that they have. I mean, that's an incredible number of cubes if you think about it, okay? Now let's talk about the vertical characteristics of this cube. And again, everybody uses the same technique, but they have different levels of granularity to them. For example, NOAA has 64 layers as they go up. Japan has 100. Europe has 137 vertical grids that stretch 50 miles high into the atmosphere. Now, they don't have a uniform height. And why is that? Well, there's a significant difference in terms of what's going on. So near the surface of the Earth, where you have mountains and valleys and oceans and dry lands and forests and all kinds of different kinds of things, these grids, the vertical height is very small. It can be as small as 10 meters. And then what happens as you move higher into the atmosphere, the vertical height of the grids increase. Well, why is that? Well, there's a lot of activity going on at the surface of the Earth that you really want to be able to keep track of and measure. And that is the thing that has the most impact on human life. But as you move into the stratosphere, you have less and less going on. And so by the time you get to the upper layers of the stratosphere, you have very, very tall, very high vertical grids. Now let's put this all together. Okay, so basically if you take a look at the image of the cube here, we have 540,000 roughly 31 by 31 kilometer cubes. The vertical cubes of those heights, we have 137 layers and it goes up to 50 miles. But what that means is the total number of cubes then that we have is basically over 74 million cubes. Let me say that again. There are 74 million cubes that they gather information in, and pretty much the same types of information in each one of those 74 million cubes. And if you look at the right-hand corner here, you can get an image of the kinds of things that go into one of those cubes. They get your radiation, wind condition, clouds, ocean heat transfer information, etc., etc. it's not just one bit of information that's going into each one of these cubes. So let's now get to the next thing. So let's talk about, well, what kinds of information goes into these cubes and where do they get that information from? So that's the next section of this presentation. And some of this, we've already shown these graphs in video 3 if you've seen it. I'm going to go through them a little bit quicker here, but I want you to pay attention to a couple of things. I want you to pay attention to the physical metrics, because each one of these individual devices are collecting different kinds of information, and they also have different transmission frequencies. And the transmission frequencies, if you look at it, really makes sense as you understand what's happening with them. It's capturing things at an appropriate pace and communicating it back, so you can really capture what's going on, but you don't have so much information that it's almost impossible to process. So that's sort of what's happening here. So let me just go through these fairly quickly. So you have the space domain, and here you have 3 different things. You have geostationary satellites, polar satellites, and GPS satellites, GPS radio signals, kinds of things. Okay. And they capture, if you look at this, they capture different kinds of information. I'm not going to go into that. You could read that slide here. And they communicate that information a little bit differently. So for the geostationary satellites, they basically remain, they move at the same pace that Earth is rotating. So they basically remain in one place. And they do that over about 22,000 miles up into the stratosphere. And they do that they communicate information then basically every 10 to 15 minutes. Whereas the polar satellites are only a couple hundred miles high, and they're sort of zooming from pole to pole every 90 minutes, but they're getting the amount of information they're getting is a very thin sliver. So they basically gather that information and report it in every 1 to 5 days what's going on. And so let's move over to the next section now. And so you have the air domain, and here you have, as we talked about before, in most of the major commercial airlines and airlines, and then the freight airlines like UPS and Federal Express, etc. They basically have these monitors in them, and they record information like temperature at different air levels, wind speeds, directions, and things like that. And and this one has a varying speed, which is kind of interesting. So as they're rising and descending, they transmit information every 10 to 30 seconds. And then once they're cruising, they only do it every 3 to 7 minutes. Why? Because there's a lot less going on while they're cruising. And then they have weather balloons, the same thing. There are basically 800 weather balloons around the world that are put up at the same time every day, twice a day. And they climb for about 2 hours. And basically, they transmit information back every 1 to 2 seconds because they're trying to measure what's happening as they go through different altitudes, okay? And then you have land and land stations, which you can see in the illustration in the upper right-hand corner there, or Doppler radar, and they have different, they measure different kinds of things like rainfall, ground level temperatures, and things like that. And they also have different transmission times. Maybe 15 to every 30 minutes for a land station. But if it's near an airport, it goes every 1 to 5 minutes because they want this information to help with airplanes landing and taking off at the airport for safety reasons. And then you have the Doppler radar, which basically gives information every 4 to 6 minutes. And then the final area we have is sort of the sea domain. And again, here you have some buoys that float in the ocean that are permanently moored, and other ones that sort of drift on the surface of the ocean. And then you have the Argo floats, which go down basically about a mile deep, and they sort of float for 9 days. Then they go down to a mile. Then they go down to a mile deep, and then as they ascend to the surface over 6 hours, They track all kinds of information. Then when they get to the service, they transmit it. And so again, you have a variety of information that's coming in from around the globe. And we talked about that in video 3, and the organization that's responsible for the communications systems that they use to communicate a lot of this information, for setting the standards for what they're going to communicate and what they track and other kinds of things, is done through the WMO. And we talked about that in video 3, and this just shows that. So now this information basically, and again, as we talked in video 3, I should say this first, the information that you're getting, or these sources, are really not owned by the WMO. They're just an organizing body. The satellites and other things, and MORS and other things, generally are owned by individual countries. In some cases, there may be just cooperation that occurs with, let's say, with commercial airlines and other kinds of things. And so the information, if it's owned, let's say, if a satellite, for example, the European satellites would communicate their information to the Bologna Processing Center, or their national centers or networks, and then they would feed the information eventually up to a regional center, and then into the main network. And if you see on this graph, you see the red stars; those represent the facilities that are at Bologna. So the regional hub is in Bologna, as is the supercenter, and there are 15 of these supercenters located around the world, such as in Beijing, Moscow, United States, etc. And they are connected on a real-time basis and share information almost instantaneously as the information comes in. So back to this sort of framework slide. So we've talked now about where the data comes from. Now what we're going to do is go to the next cycle. So now that the data has come in, we're going to talk about the resolution of this, or how this stuff gets reported. So basically the information gets reported in hour increments. And so that means in the course of a month, you will have 720 roughly snapshots generated each month. And then each one of these cubes, which will have the information that we talked about in the previous section, what they do is they capture that information, and then at the end of 12 hours, they sort of run a batch processing cycle to update the information in those cubes for each of the 12 hours in that particular segment. And so we're going to talk about that next. Okay, so here we have the Bologna Processing Center, and they go through these 5 steps with regard to this data. So let's cover that real quickly. So the first step is they really have this data coming in, and a lot of this work is done really at the regional centers, or in some cases at the national network centers. Okay, and basically what they're doing is they're looking at the data, and they're trying to make sure that the data is reasonable. And you can imagine, I don't know how many endpoints there are and how much data is coming in. The amount of data coming in, it's got to be in the trillions upon trillions, okay? Just on the fact of the amount of information they're capturing for 74 million cubes, okay? And they're gathering this data from all, there's got to be all kinds of problems occurring almost every hour of the day, timing problems and getting things here, or there may be a particular aspect may not be working quite right. And so you don't want to get this corrupted data into your system. So what they do is they have sort of formulas they've created that sort of identify what the range of expected results. And if they are way outside of that range, then they flag it and purge it and don't put it in here. Now they may follow up to get the information to see what's going on and eventually update it. But they try to make sure that this information doesn't get into the supercenter. The next thing that's going on then is you have to have standardized this stuff, okay? Because you have information coming in from weather balloons, airplanes, satellites, etc., okay? And you got to fit it into this grid, and you want to make sure that everything's in a standardized format. And so, for example, one of the things they use for temperature, they don't use Fahrenheit or centigrade, they use Kelvin. Why do they do that? Well, both Fahrenheit and centigrade have plus and minus, so you can be above zero and below zero, okay? Kelvin eliminates that. It just gets you to a single number, which you need for the computers efficiently process, okay? Or you may have information coming in knots. You need to convert that to meters per second, etc. So you have all this conversion going on, so everything's in the standardized format as it feeds into the system. Then as you feed this information into the system, another thing is going to happen, okay? If you have 74 million grids that are expecting multiple types of information in it, you're going to have, every single time almost, you've got to have some missing gaps, right? So what do you do with those? And what they do is they go in, when they have missing gaps, they go in using sort of the modeling, using scientific principles and other information they have of what happened the last time they had a reading in that, and what happens to the cubes around it, and all those kinds of things. And they basically go in and fill the cube in with what they think would be a reasonable number. The next cycle then is, there's sort of a 5-day latency here. So as this information's coming in, they allow it sort of 5 days to sort of come in and fill all these particular cubes. Okay, guys, we have all kinds of events that are going to cause delays in getting here. A ship may not get in in time. They may not be able to transmit it to a satellite. You could. There's got to be a million different problems that can go on and cause it. So they wait for 5 days to really sort of try to resolve some of these issues and make sure they have the information as accurately as possible. At the end of those 5 days, they then process it. They do it in 12-hour batches, and they basically do those batches at a time, but they're processing the information in hourly buckets, okay? And when they're done with that, they have the results. And it's called the Era 5T, which T means that it's temporary. This is the first look. And then what happens, they spend the next 2 or 3 months trying to finalize the information here to get it as accurate as they can. And when they think they're at that level, they basically do their final run. And the final run then is called the Era 5 report. The T is taken away. This is the number, and it's locked and loaded, and they will not touch it again. So as I mentioned earlier, all of this information in Copernicus is available to the general public. I was going to show some of that information, and there was just so much information available that I said I would just show you some web pictures. So the first one in the upper right-hand corner shows Copernicus, and it shows you their 6 different programs they have. And if you look at the right-hand side, you'll see if you look at it closely, you'll see Copernicus, and then you'll see the ECMWF, and then you'll see the climate change thing. And this is a portal to that particular program. And that's where all the information, the Era 5 stuff, gets put to the control store, and all of that information is available here. I just want to show you the portal for that so you can see that. Those exist for all of the other 5 programs, and once you get there, within each one of these programs, they have just multiple graphs, history, analysis. It's just amazing the amount of information. It's almost incomprehensible, okay? And then the last thing they have is they also issue reports. And I showed you the most recent one they did. They just, I think in April, or May, they issued the European Status Report of Climate for 2025. And that's available also to the general public. And this is a massive report, again, with all kinds of graphs, analysis, and other kinds of things. It's an incredible document. If you're interested in any of these things, I highly recommend you going to those websites and checking this stuff out. Okay, so this gets us back as we're wrapping this up to the slide here. And what I'm really saying here, if you look at this, this is how we calculate actual temperature. That process involves 540 horizontal cubes, 137 layers into the atmosphere 50 miles high. It produces a total number of cubes of basically over 74 million cubes, which have all kinds of information in it about wind ratio, as you can see from the diagram on the right-hand side. And this information, Copernicus, is available, is processed for every hour of every day. So that means each month you get approximately 720 of these reports out. I mean, that's just an unbelievable amount of information. So think of that, 720 reports for 7.4 million cubes with information about our climate and what's happening in the world, around the world. And then you have that just does it in processing cycles. So, and I'm going to maybe talk about it in this slide right here. I mean, there are people out there who are skeptical about climate change and other things, and I honestly don't blame them. Because really, there's a lot of people out there saying climate change is a hoax or other things, or websites you can see that say, well, temperatures really aren't changing, pointing out other things. I can guarantee you one thing. There is nobody in that group that is talking about climate change as a hoax or other things is talking about it at this level of detail with this level of granularity that probably even understands that these are how these calculations are taking place. My point. Now that gets us to the next slide, which is basically the Titanic Table. And I'm not going to go through this one because we covered it previously. I just want to say I wanted to show you how the Copernicus model works, so you can see how the information, when we talk about actual temperatures, how it's calculated. And now I want to wrap this up. And I sort of already talked about climate skeptics a little bit. And again, I just want to say this. I don't hold them at fault for their beliefs, okay? There's a lot of vested interests out there that are providing information that suggests climate change is hoax, or it's not something you have to worry about, etc., because it's maybe in their best interest on a short-term basis. And the one thing you will notice, though, that none of them have ever talked about at this level of granularity how those temperatures are calculated, right? I've never seen anything like that. And so I wanted to show this to you so you can understand where these numbers are coming from and just how sophisticated and how much information is involved in calculating these temperature numbers, folks. These are as good as anybody can get. They're real, they're accurate. I was just literally blown away by how sophisticated this process is. And so with this, I say my standard ending. I think the only way we're going to solve this problem is we need to get the net zero greenhouse gases. And the only way we're going to do that is you're going to have to get involved and do something. Because it's pretty clear to me that our elected officials aren't going to do that unless we replace them with people who believe this is an urgent issue. So I urge you to vote in every single election for candidates who believe this is a problem and are willing to tackle it. If you could, if you're interested in this, you find it interesting, subscribe, like and comment, give me comments back. That would be very helpful. And again, just thank you for spending the time listening to this video, and I hope you'll join us for some other videos.